respect to one variable. Of course, there could be functions which are variables which are functions of multiple variables, right? Multiple variables. So you could have this, right? If you have a function that's variable dependent on variables x and y, then if you would like the differentiation or the derivative of this function only with respect to x or only with respect to y, what do? You do partial derivatives. Yeah? Partial derivatives for differentiation with respect to one variable, right? So you could have a partial derivative of this function with respect to x. You could have a partial derivative of this function with respect to y. And when you do this differentiation here, you treat y terms as a constant, and when you do the differentiation with respect to y, you keep the x terms a constant. You guys know all that, yeah? And we also looked at, through some illustrative examples here, in this, air pressure scenario, you have, let's say, high pressure right about here, and then you have low pressure surrounding this space, right? Now, why is gradient important, right? So this is high pressure, let's say 100 Pascal or something, right? And there's low pressure around this high pressure region, and where is air going to move? Yeah, air is going to move from high pressure to low pressure, obviously, but it's going to move to the lowest pressure region, right? So if this is 100 and surrounding it is just 50, 40, etc., it's going to go to the lowest number. That's where the wind is going to blow. So it's a directional result, right? So the gradient, you can calculate the gradient of a field at any point. So you have a 3D space which is a scalar field, and you can calculate the gradient at every single point. And we also demonstrated this using this illustration, right? So you could be at any point. So you're on the mountain, top of the mountain. Let's say we talked about the spring example, right? So at the top of the mountain there is a spring and water's coming out, and from that initial position, where's the water going to flow? It's going to go to the steepest point. So it goes here. And from here, where is the water going to go? So you once again get the gradient of that point. So maybe the steepest descent from here is in that direction. So the water is going to go here. So the water is going to follow that path, which allows the steepest descent. And that's, even in more mathematical terms there, the vector, which gives both the magnitude and direction of the maximum spatial rate of change of a scalar function, is called the gradient of the scalar function. Just let's emphasize that gradient can be evaluated at every point in the field. Okay? Okay, and we do that, when you go hiking, you want to track the most, the most comfortable path everywhere you go. So you could be tracing a windy path, because that's the shallowest climb, maybe, right? When you're climbing, you don't want the steepest. Maybe some people do, but you want the most comfortable or the shallowest ascent. Yeah. So So you can calculate the gradient at every single point, and from every single point you can get the magnitude and direction of the maximum derivative or the maximum step change, okay, rate of change. Yeah. So now that we've in English words we've understood what gradient is, we're going to put some mathematics onto it. Yeah. So what we're going to do is we're going to define a function u, which is a function of x, y, and z. Yeah. And now this is a scalar field. Okay. Now, what are the partial derivatives in this illustration? We have partial u with respect to x. You have partial derivative u with respect to y. You have partial derivative u with respect to z. Are the partial derivatives. Okay? The partial derivatives. Now you can represent the function u x y z as a surface. So you have a scalar field or surface, right? And now you can apply some differential lengths. Yeah. So from x you go to x plus dx. So dx, dy, dz are differential lengths along x, y, z directions. Yeah. So far it's all pretty tame. Okay. Now once you've applied these differential lengths, what does that mean? You were initially at x, y, z, x comma y comma z. Now you're at a new point, a new function, which is you are at x comma y comma z, and now you've gone to x plus dx, y plus dy, z plus dz. Okay, so this is a surface, initial surface, and then you moved to the second surface. This is the second surface. Pictorially, this is what it looks like. Yeah. So this is the x, y, z coordinate system. The initial point P is on this surface U. You can see U. On this surface, the value of that function is constant, right? That's the assumption. And then you move to the next surface, which is U plus du, right? So this is U plus du, obviously. U plus du is a function of x plus dx, comma y plus dy, comma z plus dy, right? And this is what it looks like pictorially. Okay. And now we can, and this is surface 1. This is surface 2. Okay. Now you could imagine these first surface is where you are, and now you need to get the steepest descent or the steepest step change to surface 2. Yeah, so you need to get the steepest gradient. Yeah, I'm sorry, steepest differential. Yeah. So to get that, you do the subtraction. So u plus du minus u. Yeah. What would that look like? You first get the step change or the differentiation with respect to x. So this is the rate of change of the function with respect to x multiplied by the differential length dx, right? So along the x direction, the rate of change is partial du over dx, and how much is the change in x, right? So if the rate of change is 5 per change in x length, and then what is the x length itself that is changing, yeah? So you product multiply these two, and then you have the rate of change of u in the y direction, and then how much step change you have in the y direction, and then rate of change of u along the z direction, and then how much of a step change in the z direction you're taking, yeah? Now you can take this equation, right hand side, and you can write this in this format. You can say this is partial du over dx in the x direction plus partial du over dy in the y direction plus partial du over dz in the z direction. Dot product dx in the x direction plus dy in the y direction plus dz in the z direction. Yeah, so you can write that expression on the right hand side in this format. Yeah, so this is a rate of change vector. Yeah, partial derivative along the x direction, partial derivative along the y direction, partial derivative along the z direction, and then the second vector, this is simply the vector that goes from the initial point, which is p, to the final point, which is p prime, right? So initial point is p, it goes to the final point p prime. That is this vector there. Okay. Now what is this vector? Like I said, it's a vector that goes from p to p prime, right? Step change in x, step change in y, step change in z. Yeah, not nothing complex about that. Yeah. So that vector, if you look at this diagram there, that vector is dl. That vector is dl. Now we're going to call this d vector. D vector. Okay. All right. So this is the change. This is the change in the function, right? Remember, think about our altitude or elevation example, or the air pressure example. You are in a certain point in space, you have a scalar quantity, and what you need is the rate of change. Rate of change is what you need. So you go from position 1 to position 2, and you need the rate of change. So the rate of change here is du divided by dl, isn't it? Du divided by dl. So this is what you need. You need du over dl. This is what we need. So rate of change of function u, and this is a directional derivative. Why do I say directional derivative? Depending on the vector, right? Depending on which direction you take, the value is going to be different. Yeah. Now, we can write, just looking at the observing the, first of all, we've established this guy, right? So we've established that du is equal to d dot dl. Yeah. So we can, of course, expand this as well. We can say d times dl cosine theta. You can say that. Angle between two. What we can also say by looking at this diagram, what can we say? So pay attention to this triangle. So we have the vector dl going from P to P prime, right? You can see the blue trace. Now, the vector that goes from the surface u in the normal direction, which is normal direction 90 degrees to the surface u, is vector n, right? That is that vector right there. And the angle between these two is theta, right? Angle between these two is theta. Yeah.
On the diagram, which one is vector d?
The vector d is not in the diagram.
Oh, okay.
Okay. What is vector d? Vector d is the rate of change. Rate of change. How can I draw a rate of change in the picture? Right? Yeah. So we have that triangle, and we can write dl we can write dl times cosine theta equals dn. Okay, dn is a differential length along the normal vector. So by looking at this triangle, I can write dn equals dl times cosine theta. I can write that. Okay. So now what do I need? I need du over dl, right? So du over dl is what we need. It's the rate of change of the function u in a certain direction. Yeah. So we could write now dl equals dn over cosine theta on the right there. So I can write du over dn cosine theta. Okay? Once again, this is what we need. The rate of change in a certain direction. The directional derivative. Once again, is rate of change of function in a specified direction. Okay. Now, function maximum, right? That's the next step, because go back to our definition of gradient, yeah? Maximum spatial rate of change. So this is the rate of change. This is the rate of change. At what point is this value maximum? Yeah. So this function or this value is going to be maximum when cosine theta is 1. Right? That's not controversial to say. So this value here, or this variable here, is going to be maximum when cosine theta equals 1 or theta equals 0. Theta equals 0. Look at the physical significance of theta being equal to 0. So that vector dl is in alignment with dn, right? So that's when the theta angle is going to be 0. Yeah. So it's going to be max. This value is going to be max when dl aligns with dn. Okay? So, maximum rate of change of function, scalar function, occurs in the normal direction to constant surface. Okay? Yeah? And follow the train of thought here. We need the rate of change of the function, of the scalar function in a certain direction. Okay, we did that. And then what we need? We need the maximum spatial rate of change. So when is this maximum? It is maximum when cosine theta is 1, or in other words, theta is 0. What is the implication of theta being 0? dl and dn, which is the length along the normal direction, are in alignment. That's when theta is 0, that's when this function is maximum. Yeah? What does it mean when I say dl is in the normal direction? What does that mean? The direction in which this function is maximum is the normal direction. Yeah, is the normal direction to the constant surface. I said these are constant value surfaces. Okay, so the maximum rate of change of the scalar function is, let's write it in another word, maximum rate of change of scalar function u at point P, okay, is equal to normal derivative of u at point P. Okay? Let's recap or write again our definition. D times dl equals du. Yeah? What is d? D is rate of change times in the x direction, dy in the y direction, plus z in the z direction. Okay? okay? Also indicated as del u, okay? So this operator called del, okay? Huh?
Because I always thought that was a V.
Sorry?
I always thought that was a V with the line on top.
Well, that's how you write it, but it's a del. It's a symbol. It's not a letter. An operator. It is an operator. Okay? You apply this operator to scalar functions. Yeah? So this operator is a vector operator, right? You can see this is a vector. You apply this to scalar function. Yeah? Scalar function u. And the end result will be a vector. Yeah? So I think we have the, I think I gave myself too many pages for so gradient u r del u equals right? So del, the operator itself, looks like this. Yeah? Partial differentiation with respect to x along the x direction, partial differentiation with respect to y along the y direction, partial differentiation with respect to z along the z direction, and then you can apply the y inside, right? U here, u here, u here, and apply the u inside. So this is the operator applied to a scalar function. This is the operator. It's a vector operator. You see those x, y, z directions there, and this is the scalar function. Now it's a little bit meaningless to try to draw this vector because it's not a vector itself. It's a vector operator. It's a vector operator. It's like this symbol, right? It's this symbol. Standing by itself, it's meaningless. You put something here and you put something there, suddenly it has some meaning. Yeah. So it's an operator. It's a vector operator applied to a scalar function. It operates on a scalar function and results in a vector function. The gradient is normal to the constant value surface. This is what we discussed and derived by means of that diagram there. The gradient always points in the direction of maximum change in the scalar function, right? So that is the, so the definition of gradient. So if you have a, once again I can reiterate this aspect. You can have a 3D space, a 3D field of scalar function, right? So scalar fields got scalar variables. At every given point in space, in that space, you can calculate the gradient, and that gradient is the maximum rate of change of the scalar function at these individual points, right? The gradient is now going to have magnitude because it's going to tell you, well, this is 100 Pascal, the maximum step change from this point is, let's say, 30 Pascal, right? So because there is some 70 Pascal somewhere here, right? The direction component gives you where that 70 Pascal is. Yeah? So the maximum rate of change and the direction. is given by gradient. Okay, so we can do a couple of problems, example problems. They are listed in they are given in the book also. Consider the plane. So there is a plane. This is plane. When I say plane, you can see the constant value surface, right? Find a normal vector to this surface and the unit vector normal to the surface. In other words, you're going to find the normal vector to this surface and then just get the direction vector along that, unit vector along that direction. Okay? So what do we have? The function is, the equation of the plane is function of xyz equals x plus square root of 2y plus z minus 3 equals 0. Yeah? Alright? Now, what is our definition of gradient? Gradient is the directional derivative in the normal direction. Right? That's what we did when we did this analysis. Yeah? So the gradient is maximum in the normal direction. So if I get the gradient of this function, now I have the step change in the normal direction. Yeah, so the normal vector to the surface, so I can get the gradient f x y z, right? So what is the del operator? The del operator is partial d with respect to x. This whole function here, right? So x plus square root of 2y plus z minus 3. Now all of this is in the x direction. Plus, I repeat the same, but now I'm going to differentiate with respect to y. This is along the y direction. And then third step is differentiate with respect to z, the z direction. Okay? So if I perform this differentiation, what do we get? In the first term, all of these terms vanish to 0, yeah, because it's partial differentiation. So I get 1 in the x direction plus differentiation with respect to y, the other terms go to 0. Now I get square root of 2 in the y direction plus, once again, everything else goes to 0, and I get 1 along the z direction. Okay? So this is a vector, let's call it vector v is a vector normal to the plane. Okay? All right. There's a second part to that question, which says the unit vector normal to that surface. So what we need is the unit vector normal to the surface. So you can get the unit vector in the direction of this vector, right? In the direction of this vector. So you get the vector v divided by the magnitude of vector v. Yeah. What is the magnitude of vector v? Square root of 1 plus 2 plus 1, which is square root of 4 is 2. Okay? So we have 1 in the x direction plus square root of 2 in the y direction plus 1 in the z direction. Now we need to divide this by the magnitude, which is 2. So the unit vector normal to that surface is half in the x direction plus 1 over square root of 2 in the y direction plus 1 over 2 in the z direction. All right. Any thoughts, questions, concerns? So this would be one application of the gradient operator.
Professor?
Yeah.
For the exam, do we need to be this detailed for our work?
Detailed in what sense?
As in, show all of these steps?
I don't know if it is possible to do it in fewer steps.
Okay.
I mean, I haven't done anything elaborate here, right? I've just
No, I just.
differentiated.
Okay. We can't.
I mean,
use
one
short-
could, you guys could, instead of, you see here, I've written the function everywhere. That is a way for me to describe the problem to you guys, and
Of course.
somebody could write the whole thing as a, somebody could write the whole thing like that, right? This is the del operator.
Mhm.
And then they could say function. Right? Something like that.
Yeah.
Writing it down, yeah, it takes a couple of minutes. You may not have the time in a time limited exam, but it helps to minimize errors, at least in my view. Okay? Now another example problem. So this is a derivative in the direction of a vector. Now what is, let's think about this instead of just using mathematical terms here. We have the scalar field of altitude or elevation. Let's say you're standing on the slopes of a hill, right? So you're standing on the slopes of a hill. What does the gradient operator give us? The gradient operator gives the maximum slope, right? It gives the maximum slope, maximum step change is what the gradient operator gives us. And it gives us the direction. So I'm on an uphill slope, and I operate on that scalar field, which is altitudes at elevation, the gradient operator. So it now gives me the steepest elevation from where I am standing. And remember, I can calculate the gradient at the point which I'm standing on. Yeah. So it's going to give me the steepest step change. That's the definition of the gradient operator. But sometimes I don't want that. I would like to go towards the low. I would like to go in that direction. So what is the slope or the steepness in that specific direction? Okay, that's what we need sometimes, right? Depending on what we're trying to do. So what we could do is I can get the maximum steepness or the slope. What is the maximum slope? It is the directional derivative in the normal direction, right? That's the definition of gradient. So I can get the gradient, which is the maximum steepness in the normal direction, and using that information, I can get the slope in a different direction. Yeah. So what operator do we use? So we know a quantity in some direction,
and we need to know that quantity in a different direction. What operation do we use in such a need? Sorry? Somebody said something.
Is it vector addition?
Sorry?
Vector addition?
I cannot.
Vector addition?
No. So, okay, let me rephrase this. I have a quantity which I know the value of in a direction. Okay? And I need that same quantity, but not in this direction, but in a different direction.
So we use magnitude.
Well, no, it's called the projection of this guy onto this guy, right? So projection of this vector in a different direction. Yeah, so I can get the steepness, I don't even know if that's the word, I can get the slope along the normal direction, which is gradient, and then I can get, using this information, I can get the slope in a specific direction, which is dot product. I can project this vector onto a different direction. Yeah. So let's do that. So we have the derivative of the function, and let's call this function f is xy squared plus y squared z. Yeah. So we can get the gradient. Yeah, the gradient xyz is, once again I'm going to repeat this for illustration purposes, plus d over d z, the z direction, and then I have this this function here, y squared plus y squared z. So when I do this partial differentiation of that function, what do I get? Firstly, with respect to x, what happens? I have y squared, and then that's it. I have y squared. In the y direction, I am differentiating with respect to y. Yeah. What do I get? I get 2xy plus 2yz. Yeah. 2xy plus 2yz plus, in the z direction, if I differentiate with respect to z, what do I get? The first term vanishes and the second term is y squared. Alright? This is the differentiation or the gradient of the function f. Yeah, it's the gradient of the function f. Now I don't just need the general expression for gradient. Remember our hill on which we are standing. I am most interested in the slope at the point where I am standing, right? So what we need the gradient at the point 1, 1, 1. Yeah? So that would be, in the x direction I have 1, in the y direction I have 4, and in the z direction I have 1. Okay? So this is the gradient of the function f. Now what is this? This is, go back to the definition of gradient, maximum slope at point 1, 1. Alright? So if you are standing at 1, 1, you're standing on that point, the maximum slope of that field, it occurs in this direction. Yeah, it occurs in this direction, and how much is the slope is given by the magnitude of this vector. Yeah, all right. So that's the derivative of that function, the maximum value, in that at that point 1 comma 1 comma 1. So this is a vector pointing in the direction specified. Yeah. But what do we need? We need, the question is, get the derivative in the direction of a certain vector. So what do we need? We actually need this derivative in the direction of A. Okay, in the direction of A. Yeah. What is the direction of A? A itself is 3 along the x direction plus 4 along the y direction. The direction of A is the vector A divided by magnitude of A. What is magnitude of A? Then it's going to be 5, right? Square root of 9 plus 16. Yeah. So the direction of vector A, or a unit vector in the same direction as A, is given by 3 over 5 in the x direction plus 4 over 5 in the y direction. Yeah? So we've boiled the problem down to this question. I have this vector. I need the projection of this vector onto this final vector there. Yeah? So I need the projection of the vector gradient of f, yeah, on the vector A hat. Okay? So that is obtained by the dot product. That would be dot A hat. Yeah? So I have x, 1, 4 and z. 1, 4 and 1, yeah? 1 in the x direction plus 4 in the y direction plus 1 in the z direction. Dot product 3 over 5 in the x direction plus 4 over 5 in the y direction. What do we have to do in dot product? We multiply the like terms. Yeah. So we have 1 times 3 over 5 plus 4 times 4 over 5, which is 16 over 5. That's 19 over 5, or what is it? 3.8, is it? Is it 3.8 or 3.9? 3.8, yeah. Okay? So the derivative of the function given at the point 1 comma 1 comma 1 in the direction of vector A is 3.8. Okay, very good. I think this concludes our discussion on gradient. The next topic on our list is divergence. Yeah. And divergence is you will be operating on a vector, and the result will be a scalar. So it's kind of a flip of what we've just done, and we'll also take a look at what application or illustration makes sense. Yeah. Very good. Thank you. I will see you guys. Well, I won't be there at the